sac135 number 3. You get a hot chunk of copper, drop it into some room temperature water, and the question is, what's the final temperature of the water? Some heat flows out of the copper and into the water, increasing the temperature of the water and decreasing the temperature of the copper until they're both the same temperature. Then the heat stops flowing, and the question is, at what temperature does that occur? Our bookkeeping equation is that heat into water plus heat into copper has got to be equal to 0. We expect a negative amount of heat flowing into the copper plus the positive amount of heat flowing into the water is going to be equal to 0. They're both going to have the same final temperature T. Say both water and, that's a 2, copper have same final temp, which we're calling T, and it's T that we got to find. All right, let's write this down. Q W plus QC is equal to 0, where Q is the amount of heat that flows into the water for QW, and Q sub C is the amount that flows into the copper. And from our definition of specific heat capacity, we can say the heat that flows into the water is expressed by, let's see if we can find that on the formula sheet. Q is MC delta T. This is the formula that we're going to be using for this one. Pop that right in there. So for the water, we can express that as the mass of the water times the specific heat of water times the temperature change of the water. Change in anything is the final value minus the initial value. I call that temperature of the water sub 0 plus, then we got the same thing for the copper. MC lowercase c sub c. This I actually wanted to be a W over here. Times the final temperature, and I use the same symbol because I got the same final temperature for both substances, minus the initial temperature of the copper, and that's equal to 0. Note, for my definition of what I mean by delta T is final temperature minus initial temperature, this one automatically comes out positive, assuming that the final temperature is somewhere between the temperature of water and the initial temperature of the water and the initial temperature of the copper. In other words, somewhere between 25 degrees and 100 degrees. This will be positive, and this will automatically be negative. Say it turns out to be 75 degrees, we'd be talking like 75 degrees minus 100 degrees. So the fact that we've got a plus sign in here with this positive and that negative makes sense that we can indeed get 0 for that. Alright, so we just have to solve this for the temperature. Let's say we've got everything. We got the mass of the water was given as 99 grams, 99.9 grams. Specific heat of water, we can look up on the formula sheet. That's down here. Specific heat of copper, look up in the book, in your textbook. The mass of the copper, I don't think we are given. We're given the volume. We're given the size of this cube. We're told it's a cube, and we're given the side length. So if we know the density of copper, that's something we can look up. We'll look up the density of copper, and from definition, density of copper is the mass divided by the volume, and we can solve that for the mass if we can figure out what the volume is. Let's see. Kind of a side issue here. The density is equal to the mass divided by the volume, and for us this is going to be true for the copper. So the mass is just the density times the volume. It's the Greek letter rho. And the volume of a cube is just the cube of a side length, where I'm defining this to be L. And that's 2.54 centimeters, or 0.0254 meters. So I look up the density of copper in a book. I found in your textbook 8.9 times 10 to the third kilograms per meter cubed, and then times that side length of 0.0254. That's an inch, by the way. Meters. 2.54 centimeters is an inch, and then it's all cubed there. So I get for the mass of the copper that I'm going to need in that equation when I go to substitute it in as 0.146 kilograms. And those are the units, kilograms. I'm going to rewrite that. For the mass of that 1 inch cube of copper. Alright, now back to this equation. We want to solve that for t. I think I'll start by multiplying through these two expressions, trying to get t all by itself, and it appears in two different locations. I'm just going to multiply everything through so I have a whole set of terms. So I got mw cw t minus mw cw tw0 plus mc cc t minus mc cc t sub c 0, and it's all equal to 0. Now, this is a linear equation, that is to say, t appears in several places, but the highest power is 1, and there are no fractional powers. So, game plan there, just gather everything that has a t on it, in it, on the left side of the equation, everything that doesn't put on the right. So, I got the MCT for water over here, plus the MCT for copper. And then that's going to be equal to, I'll add these two terms to both sides, and I get the M. Looks like I wrote MC there, but that came from up here. This is MWCW times TW0. So let's fix that up a little bit. That's a W. So I got MWCW TW0 plus, and then the same thing for the copper. Alright, there's nothing on that right hand side that factors out, but I can factor out the MCs over here. So I got, or factor out the T, I should say. And what comes out is the MCs. There for water, there for copper, and then multiplied by T, and it's equal to that same expression. Okay, finally solving that for T, I get this big expression. So I've just divided both sides by the expression in the parentheses on the right. Don't make any silly algebra mistakes. You can't cancel the CW's and the C's and the MC's here. Try it with some simple numbers and you'll see that it's just not true. It won't be the same as the original expression if you do that. So we need this big expression, and we go ahead and substitute values with units. Mass of the water given as 99.9 grams, which slide the decimal point over 3 places to put it in kilograms. I got 0.0999 kilograms. And then CW from the formula sheet there, 4186 joules per kilogram Celsius degree. And then the TWO. Better scrunch things up a little bit here. The initial temperature of the water was 25 degrees. Let's look that up. 25. Initial temperature of the copper was 100. Okay, then plus mass of the copper, we found to be 0.146 kilograms. Specific heat of copper, I looked that up in your textbook. I also looked it up on the internet. Same value, 390 joules per kilogram Celsius degree. And then TC0, that's the initial temperature of the copper. We just scrolled up there a second ago. That was 100 degrees Celsius. And give you some parentheses there. And then I get to divide it by this sum of terms, but I got those values right up here. I can just copy them down. So copy those kind of quickly. And let me check out the units for a second. All this kilogram, joules per kilogram Celsius degree is going to cancel out with the units up here in both terms. So the units in the denominator are joules per Celsius degree with the kilograms canceling out. And then the units here are joules in each of these terms. So joules divided by joules per Celsius degree is just Celsius degrees or degrees Celsius. We can write that in either order according to whether it's a temperature or a temperature change. But our final temperature evaluates to 33.988 degrees Celsius to too many sig figs, and I'll round that off to T is equal to 34.0 degrees Celsius. I've written 3 sig figs. Every value in the calculation has at least 3 sig figs, with the possible exception of this one. We can't tell whether that's got 2 or 3 sig figs. I looked up some values in other sources for the specific heat of copper, and there was some variation corresponding to uncertainty in that last digit. So this is indeed the least significant digit, so we do have 3 sig figs in that value, so the answer should be quoted to 3 sig figs. And so our final answer for SAC 135 problem number 3 is 34.0 degrees Celsius.